Our speaker for today is Prof. Kleiner from New York.
Thank you. Thanks to the organizers for the invitation. It's a pleasure to be here. It's really nice to be here for this conference, honoring Misha and celebrating his work. So I met Misha, I think in 93, 94. I can't recall if he was at, so I was at MSRI for that year. I don't think Misha was, but he was working with Bernhard Lee, who was there. And so I think we started working on a project within a year or two. And then in the late 90s, I moved to the University of Utah for a year and a half. So I was there in Salt Lake City. And we had a very intense period where we were working together. So that was a very fruitful time for me. And I found the interactions with Misha to be very inspiring and stimulating. And it was very impactful on me, on my career. So thanks for that, Misha, if you're there. Okay, so I'm going to be talking about Carnot groups, or geometry analysis and Carnot groups. But I want to start first with a little bit of background. Okay, so I want to kind of motivate the project from kind of the big picture viewpoint. So I'm going to zoom out. The first part, just for a few minutes, I'll be talking about some context, and then I'll shift gears and kind of focus in on Carnot groups. Okay, so right, so this is really you could classify this maybe in a different sense from Dennis last time. You could classify this project as geometric mapping theory. Okay, so this is what is geometric mapping theory about? So you're looking at mapping, say f from x to y. Okay, so x and y, let's say, are metric spaces. And your mapping f is required to satisfy some kind of geometric condition, where maybe it's a quasi-isometry, maybe it's bi-Lipschitz homeomorphism, maybe it's quasi-symmetric or something else, right? And in the ideal situation, given the spaces x and y, you'd like to decide whether a map exists, right? If not, you want to prove that it doesn't exist, maybe find invariants which obstruct. On the other hand, if there are mappings, then you'd like to classify all of the mappings, right? Sometimes that's often too ambitious. So from a phenomenological point of view, it seems there's often a dichotomy into sort of the flexible case and a rigid case, right? Sometimes you see like mappings in abundance. Other cases, there are just a few, right? So that's the flexible versus rigid case. Right, so the motivation for these types of questions comes from many different strands of mathematics. So certainly in geometric group theory, I think we're familiar with quasi-isometries and such. But then there are different parts of analysis where the same kinds of questions have arisen for radically different reasons historically. So kind of quasi-conformal geometry analysis, and people who are studying analysis in a metric space setting would end up facing these geometric mapping theory questions. And then dynamical systems, well, different contexts, but certainly complex dynamics. And then, as we'll see a bit later, in differential geometry and partial differential equations. So that will come up a bit later. All right. Now, I want to say a little bit to connect this to things that are probably more familiar to this audience. Okay. So let me put on my geometric group theory hat for a minute. Right. So, suppose you have a finitely generated group. Well, there's some questions you might ask. What's the quasi-isometry group? Okay. What groups are quasi-isometric to G? What can you say about the automorphism group, or maybe the abstract commensurator, right? The abstract commensurator, you look at isomorphisms between finite index subgroups up to the natural equivalence. Or maybe you want to understand, given G, you want to look at finite overgroups G hat, where G has finite index and G hat, and try to understand those. Okay, subject to some reasonable conditions, right? So let's look at some examples, right? So a classical example, which has inspired a lot of mathematics and geometric group theory, right, is the case when you have a fundamental group of a hyperbolic manifold, right? So let's say G is a lattice, co-compact lattice in ISOM so again, at least 3, right? So, well then the quasi-isometry group of G is the same as the quasi-isometry group of hyperbolic space, right? So if you take the unit ball model of hyperbolic space, the quasi-isometry group is the same as the group of quasi-symmetric homeomorphisms of the unit sphere, which is a large group, and in particular, every diffeomorphism is quasi-symmetric. So this is a huge group. So this is kind of a flexible case. Now, if a group G prime is quasi-isometric, group G prime is quasi-isometric to G, that happens if and only if G is virtually a lattice, an ISOM HN. Now, if you want to understand the abstract commensurator of this lattice G, right? So you can look also at the commensurator of G in the isometry group. So G is the subgroup of the isometry group. Commensurator are the elements in the isometry group, so that when you conjugate, G moves to another group so that the intersection has finite index in each, right? And by Mostout rigidity, these two things are the same. So Mostout rigidity gives you this isomorphism, and then it's a theorem of Margulis, right? That the original group has infinite index in the commensurator, if and only if it's arithmetic, okay? So, and now let's look at the last question. Suppose you're looking at an overgroup G hat, so it's a finite extension. Let's say it has no non-trivial finite normal subgroups, okay? So then again, by Mostout rigidity, G hat will embed canonically in the isometry group between G and the isometry group. And so what do you know? Well, you can look at the covolume. You can look at the covolume of these lattices, and the covolume of G hat is going to be the covolume of G divided by the index, right? In particular, by the Margulis lemma, you have a lower bound on the volume of a hyperbolic manifold, right? And that'll give you an upper bound, operator upper bound on the index, right? So, okay, so let's look at maybe another example. So let's say you have a G co-compact lattice in ISOM X. Now take X, instead of being hyperbolic, let's take it to be a quaternion on a hyperbolic space. Okay? So then, right, so Ponceau has this beautiful theorem there, right? So the QI of G, that's the same as QI of the quaternionic hyperbolic space, which just reduces to the isometry group. Okay, so this is this kind of rigid situation. You can look at other examples of where X is a symmetric space. But the point I want to make here is that, all right, so let's say you don't care about quasi-isometries, right? It's perfectly fine. Let's say you really, but you care about these two questions 3 and 4, right? Somehow, if you want to approach those questions 3 and 4, the first step has to use some kind of rigidity result, okay? So, I mean, there are approaches in this case which don't involve quasi-isometries, but you have to bring in some other rigidity ingredients. Now, if you look further afield, I'd just mention a few classes of examples of groups that some people like to think about, right? So you can look at random groups, right? If you relate or density model, maybe Gromov-Thurston examples, or pinch negatively curved manifolds, Coxeter groups, Arden groups, right? In some cases, you can answer these questions, but right, and so there's been major progress in understanding quasi-isometries, but unfortunately, most of that progress is not in the Gromov hyperbolic case, all right? So if you look at say random groups or moving away from kind of special examples, say writing alert groups, there really hasn't been that much progress in understanding quasi-isometries, okay? So now, right, you do know, just in general, right, if you have a quasi-isometry F between two Gromov hyperbolic spaces, well, then you get an induced homeomorphism between their boundaries at infinity, right? And so that's not just a homeo, right? It's actually a quasi-symmetric homeomorphism with respect to the visual metrics, right? Now, if these x and x prime, these are reasonable, so they have a geometric action, So then the visual metric has a kind of approximately self-similar character, right? It's kind of has a kind of fractal structure, and therefore you're kind of led to try to study these geometric mapping problems in the context of these kind of self-similar spaces. And unfortunately, so there's been a lot of progress, but it's still rather limited. So just to give you to calibrate, right? Just take this simple fractal. This is the standard Menger sponge or Menger cube example sitting in R3. We don't know how to analyze the quasi-symmetric homeomorphisms of this, right? We don't even know that for the bi-Lipschitz homeomorphisms of this. Okay. All right. So now I want to I want to kind of shift toward thinking about Carnot groups. But the purpose of this prelude is to draw attention to quasi-isometries and say that there's still a lot that we don't understand, and it's worth trying to explore kind of the some special cases deeply, and that's what this Carnot groups how Carnot groups come into the picture here. Okay, so I'm going to shift to the narrow focus now. Let me just make a disclaimer. So I think that there's some very interesting mathematics connected with the Carnot groups. I'm not making any claim that if we understand them, then magically we're going to be able to solve all of these other questions. Okay, I just don't want to overstate anything. So let me recite some definitions. Right. So a Carnot group. Right, so a Carnot group it's a simply connected Lie group G together with a decomposition of Lie algebra into linear subspaces V1 through Vs. Okay, so these guys satisfy two conditions. Well, first of all, they should satisfy this bracket relation. Okay, so bracket of Vi with Vj lands in Vi plus J. And then the second condition is that the subspace V1, which we'll call a horizontal space, or the first layer, that should generate this as a Lie algebra. Okay? So in particular, this condition tells you that these are the Lie algebra is nilpotent, so we're looking at a nilpotent group. And then you get, from this information, you get an associated family of dilation automorphisms. Okay? So for every positive number S, you get some dilation automorphism I'm going to call delta S. So this, if you look at what this does on the level of Lie algebra, it scales V1 by the scale factor S, scales Vj by the scale factor S to the J. Okay. All right, now, so I'm going to be assuming that this first layer, V1, has an inner product on it, and I'll just assume that implicitly without referring to it. Okay, so that's going to allow us to measure the length of vectors living in the horizontal space. Okay, so examples. So the first example, the trivial example is Rn, where you just take the trivial decomposition. V1 is everything, and then the usual scaling. The first non-trivial example is the Heisenberg group, right? So you have H is the 3x3 upper triangular matrices here. And then, so you think of the Lie algebra as the strictly upper triangular matrices with zeros on the diagonal. And then you get the usual basis, x, y, and z. So the bracket of x with y is z, and then z is in the center. So the bracket of x and y with z is 0. And then this gives you the layer decomposition. V1 is just going to be the span of x1, x and y, and V2 will be the span of z. And, right, so the Carnot dilation, delta S, acts on this matrix as follows. So it scales the super diagonal guys by S and the upper right-hand quarter by S squared. Okay? Now, so a little more geometry. Right, so you can think of V1 as this subspace of the Lie algebra, but if you think of the Lie algebra as the space of left invariant vector fields on the group, then V1 defines in a natural way, a left invariant subbundle of the tangent bundle of the group, okay? And now, using that, you can define horizontal paths, right? So C1 path, say gamma, it's a mapping from the unit interval into G. That's horizontal, right? So you have this C1 path, so you can look at its velocity everywhere and just require that to be tangent to the subbundle. Okay, so that's a horizontal path. And now the Carnot distance on the group is defined as follows. So the distance between 2 points P and Q, you get by looking at horizontal paths gamma joining P to Q. So it's not hard to see those exist. Well, they exist. And then you can look at their length. And so the length, right, so for every time t, the velocity of gamma is tangent to v1. That has a norm on it, so we can take its length to get the speed, and now we integrate the speed to get length. So that defines this, and then we infimalize to get the distance. Okay? So, right, just from the setup, right, this gives us a distance on the Carnot group. It's invariant under left translation. It's also, it scales nicely with respect to the Carnot scaling, right? So the Carnot group looks as if it's trying to be Euclidean space, right? Because it's homogeneous and scale invariant, but it's not quite Euclidean, right? So the Carnot group G, this will be a manifold. This dimension is equal to the dimension of the Lie algebra, which is just, you look at the dimension of the ith layer and sum over I, okay? But metrically, it's different, right? Metrically, it has Hausdorff dimension equal to nu, where nu is the homogeneous dimension, right? So if you look at a ball of radius r, you look at the nu dimensional Hausdorff measure, that's just r to the nu, up to a constant, okay? And here, what is nu? Well, for nu, you take the dimension of the ith layer vi, multiplied, weighted by I and sum over I, okay? So for example, the Heisenberg group, the first layer is two-dimensional, the second layer is one-dimensional, so the homogeneous dimension is 4, and the Heisenberg group behaves metrically like something four-dimensional, right? Okay, now, so where do these things show up? Well, so you can get them as follows. Let's say you take a finitely generated nilpotent group. You take a generating set, or word metric, okay? And then you take an asymptotic cone, right? So you take a sequence of scale factors going to 0 and pass to an ultra limit or Gromf-Hausdorff limit. By theorem of Ponceau, what you'll get is a Carnot group, okay? I'm lying a little bit. You may get a Fensler metric and not Riemannian, but basically that's correct. Likewise, if you take, instead of a finitely generated group, if you take, say, a simply connected nilpotent Lie group with a left invariant Riemannian metric, scale that down, again, you get a Carnot group. So you can get these as kind of blow-downs or tangent cones at infinity. Now, in other contexts, you can get them as blow-ups, okay? So if you, in subriemannian geometry, you're given a smooth manifold, and then you specify a subbundle of the tangent bundle, right? So, and then you put a metric, an inner product on that subbundle, and then you can define the Carnot metric the way I did before, okay? Now, under some non-degeneracy assumptions, the term is equiregular, Gromov showed that for these metric spaces, if you blow up at any point, right, so you choose a point, you take scale factors going to infinity, you can pass to a limit, a pointed Gromov-Hausdorff limit, and you'll get a Carnot group. Okay. So another way that these show up is when you're looking at negative curvature. Okay. So if you think about a homogeneous space, right? So a Riemannian manifold with a transitive isometry group, right? So if you have such a guy and it has negative sectional curvature, so these were basically classified by Heinze. They have a very simple structure, okay? All such manifolds you can obtain as follows. You take a simply connected nilpotent Lie group, okay? You take an action of R on that by scaling automorphisms, okay? Say contracting automorphisms, you form the semi-direct product, okay? That will admit a metric with negative sectional curvature, okay? So the simplest case is when you take a Carnot group, let R act by the Carnot dilations, form the semi-direct product, okay? So, and the simplest case of that is hyperbolic space, where you let R act on Rn by just the usual scaling, okay? And you'll get the kind of upper half space model for hyperbolic space, all right? Okay, so now I want to mention a couple of other examples. So these should, I don't want to give you the impression that these are somehow representative. These are basically like the simplest variations on the Heisenberg group you could come up with, okay? So the first is the mth Heisenberg group. So HM, so this is going to be a two-step Carnot group. So the first layer is just complex n-dimensional space, okay, CM. Second layer is R, okay. Only non-trivial brackets are going from the first layer to the second layer, and this is just the imaginary part of the standard Hermitian inner product, okay. Now a variation on that, let's replace the complexes by the quaternions, okay. So the first layer, instead of being complex n-dimensional space, is quaternionic n-dimensional space. The second layer is the imaginary quaternions, which we'll think of as R3, and then the bracket is just the imaginary part of the standard Hermitian inner product on the quaternions. Okay, so this, so that's a description on the Lie algebra level. The corresponding Carnot group is usually called the quaternionic Heisenberg group, and if you use this Heinze construction, you get quaternionic hyperbolic space. Okay, so so another variation on this is just to take the mth Heisenberg group and complexify. Okay, so you complexify. So if you look at on the Lie algebra level, you complexify the direct sum decomposition. This gives you a complex Lie group. And so the last example is to replace the 3x3 upper triangular matrices with the n by n upper triangular matrices. Okay, so here, right? So the Lie algebra would just be the strictly upper triangular matrices with zeros on the diagonal, and the jth layer, right? So the first layer, V1, just corresponds to the matrices where the non-zero entries are restricted to the super diagonal here, and the jth layer is the guys whose non-zero entries are restricted to the jth super diagonal. Okay. So okay, so those were just a few examples. I said those should not be considered representative. Okay, so now a little bit about mapping. So I want to look at mappings. Say F from U to U prime, where these guys are U and U prime are open subsets of Carnot groups G and G prime, which may be Lipschitz, they may be by Lipschitz depending upon the context, or quasi-symmetric, or satisfy some other condition. And these are the metric conditions defined with respect to the Carnot distance. Okay. Now, just to recall, so a map is quasi-symmetric. The map is F is quasi-symmetric if you have some homeomorphism eta from the non-negative reals to itself, usually called the distortion homeomorphism, and it has the following property. So basically, it distorts distance ratios in a controlled way. Okay, so if you take a triple of distinct points px, y in the domain, right? So you can look at this quantity here, the ratio of the distance from p to x to the distance from p to y. Okay, and you look at the corresponding quantity in the target. The quantity in the target is controlled by the quantity domain via this distortion function eta. Okay, so the simplest examples are by Lipschitz homeomorphisms. Okay, but in general they don't have to be. Just x goes to x to the alpha, where alpha is a positive number on the reals. That's quasi-symmetric, but it's by Lipschitz only if alpha is 1. Okay. Now these guys have been studied for a variety of different reasons for a long time, and so in the Euclidean case for a long time, and since 1970, in the work of Mostow, they showed up in the Carnot group case. So how do these show up? Well, if you take a quasi-isometry between two nilpotent groups and pass to an asymptotic cone, right, then you'll get by Lipschitz homeomorphism between the asymptotic cones, which are Carnot groups, as I mentioned before. And then another case would be you look at a boundary homeomorphism that's induced by a quasi-isometry, right, where these guys are negatively curved homogeneous spaces. Okay. So just a remark. So just from these constructions, the mappings you get are maybe they're by Lipschitz, maybe they're quasi-symmetric, but in general they don't have any better smoothness properties than that. Okay, because they come from some limiting construction. Okay. So, so now I want to focus on this mapping problem, right? So I want to understand quasi-symmetric homeomorphisms between open sets in these Carnot groups. Okay, that's kind of the general problem. Now, let's start out with a toy case, just to kind of warm up and get started. Let's think about the case when F is actually a smooth diffeomorphism. Okay, so so there's a fairly easy observation, right? If you have a C1 diffeomorphism between open subsets of these Carnot groups, then it's going to be locally by Lipschitz with respect to the Carnot metrics, if and only if it's locally quasi-symmetric, if and only if the mapping F is contact. Okay? What does contact mean? Just means F is a diffeomorphism, it should preserve the horizontal subbundle. Okay? So it means, right, so contact means for any point X in the domain, you look at the horizontal space, V1 of X, that's a subspace of the tangent space, then you apply the differential, you get a subspace of the tangent space at the image point, and that should agree with the subbundle at that value, right? So just simple geometric condition. Right, a vector field is contact if it's flow by contact diffeomorphisms. So just a caveat here, right? I guess everybody's heard of contact topology or contact geometry. This is a rather substantial generalization of that notion, right? If you're looking at the Heisenberg group, then it coincides with the notion from that you hear symplectic geometers talking about. But this is more general, okay? In any case, once you have this observation, right, if you're looking at the smooth case, right, so now the question becomes, like, what are the contact diffeomorphisms, right? So let's look at some examples. Well, in Rn, being contact is a vacuous condition because the horizontal subbundle is everything, right? So that's kind of vacuous. What about the Heisenberg group? So it's an easy calculation in differential geometry. You can produce an infinite dimensional space of contact vector fields, and you can classify them easily. And their flows give you like a large supply of contact diffeomorphisms. But let's look at, say, the case of a product, say the product of the first Heisenberg group with itself, and looking at contact diffeomorphisms there. So it's the theorem of Cowling and Riemann. Those guys actually are products. Okay. So in fact, they must preserve the product structure, so they're going to be products of contact diffeomorphisms between factors. Okay. Now, if you look at the holomorphic version or the complex version of that, look at the contact diffeomorphisms from the complex Heisenberg group to itself. These guys show that those guys are actually holomorphic or anti-holomorphic. Okay. And if you come back to the example that I mentioned before, of the quaternionic Heisenberg group, here the contact diffeomorphisms form a finite dimensional family. Okay, which is first discussed by Tanaka, and then it also shows up in Halsey's work. Okay, so just those are some examples to give you a sense of what this contact condition looks like, right? You can see the behavior is very different in these different cases. In general, right? In general, the condition of being contact is just a partial differential equation, a first order partial differential equation on the mapping F. Okay, it's a system, and so it's formally overdetermined. Unless you're in these very special cases here. And, right, so the standard method for handling systems of PDEs like this goes back to the 19th century. What you do is you look at the system and you differentiate it. Okay, you replace the system with the associated system on the derivatives, and you keep going, and typically each time you differentiate, you get more constraints. Okay, so this process is called prolongation. When you're in the theory of exterior differential systems, and so this was studied more than 100 years ago. There was a series of papers by Élie Curtin in the first decade of the 20th century. Those were not very well understood for a long time. People came back in the 60s trying to understand what he did, and then after Ponceau's work on quasi-isometries, there was another burst of activity. Okay, so in any case, I don't want to drill into this, but the point is that the method it give you what you end up with is a general procedure for understanding contact diffeomorphisms for a given Carnot group. But it's based on the theory of exterior differential systems, which is based on Cartan-Kähler, so it really only applies to real analytic mappings. Okay, so just maybe two takeaways from this. So this general theory, I mean, it's rather an intricate story, but so there's a dichotomy for these exterior differential systems into systems of finite type and infinite type, where the dichotomy is whether locally, if the solutions depend on finite and many parameters, locally they depend on infinite and many parameters. Okay, so that's kind of a general dichotomy for exterior differential systems. And in this case, those two cases are called rigid or non-rigid by Otazi, Warhurst, and others. Okay, so I'm going to use that terminology. So the Carnot group is rigid, right? If locally you see finite dimensional family of solutions to this contact problem, and non-rigid otherwise. Okay, and I note that in the non-rigid case, this contact system is really, the behavior is very different depending upon the groups, and they don't have to fall into any conventional PDE classification. Okay. All right. So now let's come back to the. So that was the easy case. So let's come back to the original question about quasi-symmetric homeomorphisms. Right. So we're looking at a quasi-symmetric homeo between open sets. And so this discussion that I just mentioned about exterior differential systems, it breaks down completely, okay? Because the mappings are a priori not even differentiable, okay? But this is actually a completely standard situation in PDE theory, where you often end up with solutions to your PDE. They're just weak solutions. They don't have regularity a priori, and a big chunk of the literature is relates to regularity issues. Okay, and in this case, so you have kind of two variables to think about. One is the particular system that you're looking at, and analytically, the behavior can be quite different, as you just saw from the examples a minute ago. But then you also have another variable, which is the regularity that you assume of the mappings. Okay. Okay, so now I want to look at some specific cases and start stating some results. So the first, I think the simplest to appreciate maybe is product rigidity. So let's say we take two open sets, U1 and U2, in the Heisenberg group. Okay, and then we look at this kind of rectangle, U1 cross U2, and suppose we have a quasi-symmetric homeomorphism from that to some other open set U prime. Okay. So then this F is a product, right? So this is just a special case of a general result of the product. Note I stated essentially the same result a few minutes ago, but for smooth diffeomorphisms. Okay, but the proof is completely different. So let me give kind of an indication of the proof. So the first ingredient here is Ponceau's differentiability theorem, which is a version of Rademacher's theorem. Rademacher's theorem says that if you have a Lipschitz function on Rn, it's differentiable almost everywhere. Okay, so Ponceau's theorem is kind of a version of that in the Carnot group setting. Okay, so so let me just recall that. So let's say you have a map between open subsets of Carnot groups. Okay, and let's say you pick a point x in the domain and some number r. Okay, so then we can take the mapping F and we kind of recenter, centered at x and recenter it at the identity. Okay, so Fx is just the original map F pre and post composed by left translations. Okay, so the x becomes the identity and Fx becomes the identity, and then Fxr, well, we conjugate. So Fx is this recentered guy, and then we conjugate it by scaling. Okay, so we're basically recentering the map and dilating. Okay. So the map F is Ponceau differentiable at this point, if the following holds, if these rescalings, you look at fxr, these converge to a nice limit, which will be a group homomorphism, or in fact a graded group homomorphism from G to G prime, okay? And this convergence should be uniform on compact sets. So if you unwind definitions, if you replace G and G prime with Euclidean space, this is just the usual notion of differentiability, and you end up with a linear map, okay? So here, right, so a Lie group homomorphism is graded if it commutes with dilations, okay? Which is the same thing as saying that it respects the layer decomposition, okay? So Ponceau showed that if you have, say, either a quasi-symmetric homomorphism or a Lipschitz map, then it's differentiable almost everywhere in this sense, okay? So this is a version of Rademacher's theorem in this setting. And in the quasi-symmetric case, then this graded group homomorphism is actually an isomorphism almost everywhere, okay? So let me just remark for people who are, I'm largely trying to hide the analysis, I apologize for that. You know, the idea here is use the quasi-symmetry condition to first show that the mapping has some kind of Sobolev regularity, and then it's really, the Sobolev regularity is used to prove the differentiability, okay? Okay, so now let's come back to our question, right? We have, let's say we have a quasi-symmetric homomorphism from H cross H to itself, right? So then, right, so by Ponceau's theorem, we know that for almost every point x in H cross H, we can look at this Ponceau differential, right? And this is going to be a graded isomorphism between these two Carnot groups, okay? So it's an easy lemma to see that such a graded isomorphism is actually a product of graded isomorphisms, meaning either it sends the first factor to itself and the second factor to itself, or it interchanges them, okay? So we end up with the following, right? So where this is defined, if you apply the Ponceau differential to say the first factor in H cross E, right? Then the image is either the first factor or it's the second factor. Okay, so they're just these two possibilities. Okay, and so it's not hard to see that if this Ponceau differential varied continuously, right? Well, then you'd end up the image of this horizontal space would have to be making a continuous choice between two discrete alternatives, right? So it would have to just make a fixed choice, right? But unfortunately, the Ponceau differential is only measurable, okay? So it turns out that the crux of the proof is to rule out the possibility that this Ponceau differential is somehow measurably oscillating between these two cases, right? Preserving the subspaces and interchanging them, okay? So let me think about a toy problem where the same kind of behavior might arise, okay? So let's think about the Euclidean problem where we have maps whose derivatives have this kind of behavior, okay? So let's say we have in Rn two open connected sets, omega 1, omega 2. So then I'll say a mapping F from the product to Rn cross Rn, it splits, or splits as a product, if it's a product of mappings, right? So again, that just means that it's either a product in the obvious sense, or maybe it's a product after you interchange the factors, okay? So, and now, let's say we have a mapping satisfying some kind of regularity condition, maybe it's Lipschitz or Sobolev. And the question is, if the derivatives have this splitting property, so almost everywhere, if the derivatives preserve the product structure, or they preserves factors or interchange them, does that mean that the map itself has that property, right? So does this splitting property of the derivatives, is that inherited by the whole mapping? Okay, so this is kind of the situation we were in a moment ago in H cross H. Okay, so this turns out to be a more interesting question than you might initially expect. So the answer is yes. So if you're in Rn for n at least 2, so the mapping is in dimension 4 or higher, okay? And your mapping is in W1 too, so that means the derivative is at least locally square integrable. In particular, this would apply to quasi-symmetric mappings. Then the infinitesimal product structure is inherited by the map globally. Okay, so these mappings would split as products. But if you go below exponent 2, then you can find counterexamples. Okay, in dimensions 4 and higher. And then in dimension 2, right? So n equals 1. So you're looking to map from R cross R. Things are even more bizarre. Okay, it turns out you can find a Bilevschitz homeomorphism from R2 to itself with these properties. So first of all, the derivative is split and it's bijective almost everywhere, right? So at almost every point, it maps x-axis to itself and the y-axis to itself, or it interchanges them. Okay, but the mapping F does not split as a product. The mapping is even area preserving almost everywhere. And furthermore, the derivative takes on only 5 values, modulo null set. Okay, so the punchline here is that this property of having oscillation of the derivatives can really arise. Okay. Okay, so let's come back to, I just want to say a little bit about the theorem, the proof of the theorem, right? So let's look at this rigidity result first. So let's take the case n equals 2. So we're looking at a mapping F from R2 across R2 into itself. And okay, so now I want to show that the derivative cannot oscillate in this weird way. Okay, so let's look at the let's use the pullback. Let's use the differential to pull back a differential form, right? So this differential is defined for almost every x, right? So we can look at this coordinate 2 form, dx1 wedge dx2, just pull it back, okay? So that's not defined everywhere, but it's defined almost everywhere, okay? And at every point, there are going to be 2 possibilities, right? If I take this dx1 wedge dx2 and I pull it back at a point where the differential preserves the 2 coordinate planes, then it's going to get pulled back to a multiple of itself, okay? If I pull it back at a point where the differential interchanges the 2, then dx1 wedge dx2 is going to get pulled back to a multiple of dx3 wedge dx4, okay? So the upshot is that when I look at the pullback form, I get something which is a linear combination of these two forms, dx1 wedge dx2 and dx3 wedge dx4, with coefficients, let's call them a1, 2, and a3, 4. These are measurable, okay, and they're non-zero and disjoint measurable subsets corresponding to the sets where the derivative preserves or interchanges the set spaces, and their union has full measure, okay? So that's kind of just unwinding the setup. So now it turns out that since this form is closed and this F is in this Sobolev space, there's a theorem for Shetniak which tells you that this pullback form is weakly closed. Okay? So what do I mean by that? Well, I just said that, I mean, this mapping F is not smooth, right? So you can pull back the form, you're just going to get a measurable form. So you can't take exterior derivative in the usual sense. Okay? But there's a distributional notion of exterior derivative, and this applies here. Okay? So that's what I mean when I say it's weakly closed. So just do a simple calculation. We pull back this form by F, so that's closed, so D is 0. Okay? Now this form, the pullback has this structure, and now when you take the exterior derivative of the first term, okay, so you get this and that. Now look at this guy. When I take the exterior derivative here, I'm going to get the derivative a12 in the first coordinate direction times dx1, right? But that's getting wedged with dx1 wedged dx2, so that dies. Okay. So in this first term here, of the 4 terms, you're only left with these 2 here. Okay. The derivative in the third coordinate direction and d4. Okay. And likewise for the second term. Okay. So the point is, if you look at this expression, what you see is a linear combination of 3 forms, And those are three distinct preforms. They're linearly independent, okay? They're linearly independent, and this linear combination vanishes, and therefore the coefficients are zero, okay? That's really the punchline. So you get that therefore the coefficients are zero, so these distribution derivatives are zero, which basically says this A12 is constant in the vertical direction, and similarly the A34 is constant in the horizontal direction. So these sets S1 and S2 and S34 have this kind of structure up to null sets, and therefore one of them, since their intersection is null, one of them has to be empty. Okay, so that's basically the proof. Okay. Okay, so let me forget this. So the proof in the case we started with H cross H, it follows a similar outline. Except that you can't just use pullback in the usual sense because these mappings are not differentiable in the usual sense. You have a Ponceau differential, which you can try to use to define a pullback. So you have a notion of Ponceau pullback, which looks formally the same, right? At a point X, the Ponceau pullback of some form. You just take the Ponceau differential, right, at the point where it's defined, and use that to pull back the form at the image point. Okay? So this sounds good. However, it turns out that this notion of Ponceau pullback doesn't commute with exterior derivatives, even if you have a smooth contact mapping. Okay. However, I mean, in the end, it turns out there's a version of Reshetnik's theorem, but I mean, roughly speaking, the idea is these guys don't commute in general, but if you look at specific forms and pull back, then it sort of partially holds. Okay. So. All right, so let me, okay, so I'm running a little short on time, so let me skip over a little bit of stuff. So the theorem I mentioned before has a generalization that looks similar to what we just saw for these mappings in Rn. So you don't need the mapping to be quasi-symmetric to which is Sobolev. So now I want to say a little bit about this version of Reshetnik's theorem. Okay, so as I said, it's like saying that Ponceau pullback commutes with exterior derivatives, but only for certain forms. Okay, so I want to explain what those forms are, and that relates to something that was defined by Riemann some time ago. Okay, so for a general Carnot group, Riemann defined, right? So you look at the de Rham complex on the group, so omega star of G, and he defined a descending filtration of the de Rham complex by differential ideals. Okay, so what does that mean? So that means these are subcomplexes, right? So they're closed under the exterior derivative, and they're closed under wedge product with forms. Okay, so that's so he defined this filtration. And let me say what this is. It's not hard to do. Right, so you start with the right. So the Carnot dilations act on the Lie algebra in a diagonalizable way, so preserving the layer decomposition, right? And then you can look at the induced action on the exterior algebra, the wedge G. That's also going to be diagonalizable. And okay, so that leads you to a notion of weight. Okay, so for a number of W between 0 and the homogeneous dimension, the subspace of elements of weight W will be defined as follows. So wedge K comma W. Well, these are just going to be the elements in the kth exterior power with a property that when you pull back by the Carnot dilation by S, you get back the same form multiplied by S to the W. Okay? So, so these are basically, as W varies, you get kind of eigenspace decomposition. And then the subspace of weight bigger than or equal to W is just the direct sum of these guys where W bar is bigger than or equal to W. Okay? And now the Riemann filtration is defined as follows. So FW, that's just the guys, those are the differential forms which take values in this subspace of the algebra at a root point. Okay? And Okay, so the pullback theorem reads as follows. So if you have Carnot groups G and G prime, G has dimension n and homogeneous dimension nu, okay? And now suppose we have a map F, which is W1P, where P is strictly larger than nu. In particular, if you have a quasi-symmetric homeomorphism, this would be satisfied. And now let's take two forms, omega and eta, of degree k and L. Eta should be compactly supported. So the degrees are complementary but one, okay? So k plus L is n minus one. And then you have a further condition, which is a condition on the weights, okay? So if you look at the total weight of d omega and eta, that should be at least nu, and likewise for omega and d eta. And then under those conditions, what you get is the following, that if you, if you take the Ponceau pullback of d omega, wedge it with eta and integrate, and then you do it in the other order, you get 0, okay? So formally speaking, what this is saying is that if you look at the commutator of Ponceau pullback with the exterior derivative, you apply that to form the form omega satisfying this condition, and then you pair it with the form eta satisfying this, then you get 0. Okay, so it's saying it sort of partially commutes. All right, anyway, I wanted to at least state the pullback theorem because now I'm going to mention a bunch of results which start from the pullback theorem and then you apply, then you work from there. Okay, so first of all, for the complex Heisenberg group, if you have a quasi-symmetric homeomorphism, more generally the Sobolev mapping, where the Ponceau differential is an isomorphism almost everywhere, then it's locally holomorphic or anti-holomorphic. Okay, so this was the result that we saw before under this, starting with the assumption that you have a smooth mapping. Okay. Now, okay, that's short on time. All right, I think I'll skip this result. So we have it's kind of a structural result about quasi-symmetric homeomorphisms in a non-rigid case, but I'm going to skip that. And look at the rigid case. Remember, these are the Carnot groups where if you're studying the smooth mappings, the contact mappings, then you just see those belong to a finite dimensional family. Okay, so there's a conjecture here. Natural conjecture is that if you have a rigid Carnot group and a quasi-symmetric homeomorphism, then it's actually smooth. Okay, in which case you can understand what it is by using that classical theory. Okay, so this was known by work of Ponceau and these guys, right? Under the special case that the graded automorphisms act on the first layer conformally. Okay, this was proved using subelliptic regularity. So let me just mention one case here. And that comes back to this sort of simple example of the upper triangular matrices, right? So let's look at this Carnot group of upper triangular matrices in GLNF, okay? And suppose you have, for P bigger than nu, you have let's say you have a quasi-symmetric mapping between open subsets, then it's actually smooth, okay? So this solves the regularity conjecture in this case. So you can think of this as kind of a version of Ponceau's theorem for this kind of manifold, this flag manifold associated with this group. Okay. All right. So let's skip this quasi-regular mapping stuff and look at contact manifolds. So now I'm talking about contact manifolds in the sense understood by symplectic geometers. Okay. So if you have a contact manifold, so that's where you have the subbundle has codimension 1. So there, Roumain had defined so used this subbundle to define a kind of an adapted version of the de Rham complex, okay, called the Roumain complex. So it's a cochain complex that you can kind of cook up from the de Rham complex using this subbundle, okay, and so. So it naturally leads to you can there's a version of that using forms with distributional coefficients that gives you this cochain complex, which I'll denote by this. So using a pullback theorem, we can show that these, say, quasi-symmetric mapping or Sobolev mapping actually induces a chain mapping between these complexes. Okay, so that this natural adaptation of the Durand complex to contact manifolds is respected by these mappings. Okay, so there's another correlate that comes out of this, right? So there's what I'll call the flat Riemann complex. So this is where you look at the elements which have bounded coefficients and whose differentials have bounded coefficients. So we call these the flat Riemann complex because it's the analog in the contact case of Whitney flat forms. And so using the same pullback theorem and a little work, you can show that Ponceau pullback actually induces an isomorphism of these cochain complexes. Okay. So this Riemann complex is kind of Bi-Lipschitz natural cochain complex. And then moving more generally to the setting of Carnot groups. So people were wondering if there's some version of the Riemann complex for a more general Carnot group. And it turns out this same pullback theorem gives you the answer to that question. Okay, so so you have this Riemann filtration of the Durand complex that I mentioned before. But as soon as you see this kind of descending filtration of cochain complexes, there's a standard algebraic construction for a spectral sequence. Okay, and so it turns out that so the same pullback theorem tells you that, again, you start with say quasi-symmetric mapping or W1P mapping, then it induces a mapping of spectral sequences. Okay, so this is kind of it's a standard situation, right? If you have a chain mapping between cochain complexes, between filtered cochain complexes, and the chain mapping respects the filtrations, then you get an induced mapping between spectral sequences. This is a standard algebraic construction. What's strange here is the mapping F is not a chain mapping. It's filtration preserving, but it's not a chain mapping. But somehow you end up getting an induced mapping between the spectral sequences. So that seems to be the natural replacement for the Durand complex in this general setting. Okay, so I'll stop there.
Any questions?
In the product case, what misses between P larger than 2 and P smaller than 2 is the Reshetnev theorem?
So in a positive direction, getting rigidity, that's the borderline case for Reshetnev. In the other case, we have this convex integration argument that just works for P's as long as it's below 2. Yeah.
Just to understand the definition, if you take the Fresnel bottom group and then take its Marxan condition, it's a Carnot.
Yeah.
In this slide, like the last exotic example, how is it constructed? Like how does it look?
So, okay, I said I was trying to avoid the analysis. So this is, it's constructed by convex integration. A lot of that's a term that goes back to Gromov in, I think, the 70s or 80s. At least in the rough outline, it follows this convex integration strategy, but it's probably hard to say much without saying a lot beyond that.